mean this class as well as evening class of 5, I think we will be doing the actual design of an OPAMP. So those who feel that is not relevant need not come in the extra class, but today is the day when I will actually show you how to evaluate for given specifications, how do you make a choice of different WLs. Okay, so coming back to the issue which again will be used in the OPAMP design is the stability issue. Please remember, as I keep saying by joke that when you design an amplifier, you tend to find that it does not work an amplifier, it acts like a growing system, instability grows, and vice versa occurs when you want oscillator to work, it does not oscillate at a frequency, it damps down. Okay. So the issue of probability is related to something feedbacks, and we have been looking into feedback for quite some time. I may quickly say the closed loop gain, that is there is a feedback available which has a beta network, and in this case the beta is also a function of frequency, like a capacitive will always be a function of frequency. So beta is also a function of S. In the amplifiers which we designed earlier in our earlier second year classes, there we always show that series resistance, series feedback through R source resistance, or so we always took a very simpler situations, but in internal circuits like OPAMPs the capacitance will play dominant role, and therefore beta is not constant like R2 by R1 plus R2 kind, but it will be something like a function of frequency. We also defined that the loop gain is called the AS into BS, call it A0 if you wish. I think that 0 stand for open loop gain, okay, not the DC gain, it is an open loop gain, maybe you should write OL. Then at any frequency the loop gain can be written as A0 j omega into B j omega, and in a phasor, I suppose all of you know phasors, the magnitude e to the power j phi omega is the phasor representation of this function, and where phi omega is the phase angle. Now if I really see clearly that at a given frequency omega 0 and I figure out this phase omega at that frequency is 180 degree, then we figure out that this loop gain at that frequency is essentially minus but real, because there is no cos 180 sin 180 cos 180, so it is minus 1, and therefore this quantity is real and negative. Now if you can see what is happening, if this quantity is negative and real, which is what this phasor is telling me at a given frequency, I am just trying to recapitulate what we did or what we did not do correctly or otherwise, or what you learned in second year. The reason why I am interested in doing this kind, because ultimately there are number of ways stability criteria can be tested for any second or third order transfer functions. Control theory course, if you are already doing it or have done it, you are well aware of all other techniques, root locus techniques or the Nyquist criteria or T methods, but we are interested to show only one method, which is the Bode's plot method, because it gives you some direct relationship with the components which we are going to use. No one to say that those techniques will not result into same, but this is only to take case that we are only looking for Bode's plots. Okay. So for the Bode's plot, all this analysis is done only for the sake of finding out when stability has or when does not have, is decided by looking at the Bode's plots. So if you see this quantity is negative and real, obviously denominator is going down because that quantity is real, and if this quantity is real, obviously closed loop gain is higher than open loop gain, okay, which essentially means that the growth is starting. Okay, that means closed loop gain normally should be less than open loop gain, but in this case if that happens at that degree 180 degree above, we will figure out that this quantity will then push closed loop gain higher, and we say instability is set in simply because positive feedback has started. So obviously if I do not want positive feedback to occur, so the loop gain maximum, the degrees up to which I should go is 180 degree or preferably lower, so that this positive feedback does not come into, that is the stability issue. Okay. Typically if you plot the loop gains for magnitude and phase, one can show that this is the standard Bode's plot for loop gain versus frequency in log scale, same way omega versus phi j omega goes from 0 to 180 degree, and this 180 may come from the network, 180 come from the phase of the amplifier itself. So in phase component may start increasing as feedback increases, and therefore more and more growth can be actually seen, instability occurs. So now how do I get rid of this, or how do I figure out that I am safe? Okay. So that is what the condition which we are going to show. If the beta network is constant, that is resistive, then it is much easier to see from the Bode's plot how much is that stability issues are, but if it is not, then probably you should plot loop gains. Okay. I will show you the other figure also. Just note down, I think these are very trivials. Okay. Just to show you, typically there is a pole, and right now I am showing only single pole system. You can have multiple poles and we can have two slopes down. Okay, a 20 dB per decade may become minus 40 dB and third may get minus 60 dB, but this is just to get a single pole, and this is the wave phase associated with this. So if I really plot for a given case for a say two pole system, this is called second order system which has a feedback, and if I plot loop gain in dBs versus log in frequencies, the first pole occurs somewhere at P1, okay, and that is our bandwidth, okay, and then the way it is chosen right now is this pole all the way, a single pole is occurring till the gain bandwidth point is reached, that is 0 dB gain is achieved. Beyond that, let us say second pole occurs at GBW, okay, at, it may occur earlier or it may occur later, but this is the mid case where the second pole starts at GBW itself, then the fall will be minus 40 dB per decade, 20 from this, 20 from the other, and if you now see, if you plot this into the, in the case of phase values, at every pole we know 45 degree it should show from 0 to 45. So it shows, since it is shown from minus of this, I am starting from 180. So somewhere at the pole it must go 45 degree down from this maximum value 180. So at 135 this is the pole. Until the second pole occurs, there is no another fall should occur, so it should keep constant. But at this point you want another 45 degree from here, that means at 45 degree this point must get hit, which means the slope will be then 90 degree, like 45 degree per decade. So in 2 decades it will reach phase of 0 degrees. Now this essentially is trying to tell that when the gain bandwidth product point or GBW point, that is the loop gain is 0, at that time the phase is not 0. Phase is not 0, but it is some positive quantity shown here. What does this essentially means? It is essentially trying to tell you that before this reaches 180 degree, when the positive feedback starts, the gain has already become negative, so the numerator will start increasing because gain itself has become negative, because phase has appeared already from there. In this case gain was positive, and if 180 point occurs, then there is the issue of positive feedback to occur. So one can see from here, I can have the second pole start from here, or I can have second pole start from somewhere down. Of course it may still pass through this point. The point is, if the second pole occurs somewhere earlier to this, that means 45 point will come somewhere here, and then it is likely that GB by that time it would have crossed 180 degree, because if it is occurring earlier at 135, next 45 down it may reach 180 even before gain bandwidth point is reached, which means you are guaranteed in positive feedback system because gain is still positive, okay. So this means the minimum, I should not say minimum, the safest point, because 45 degree is from here, that means the safest possibility is that phase margin what we declared is this value should be at least 45. Somewhere here also it is safe, I am not trying to say, but you do not know how much pole is then away from this, may decide whether you will come very close to GBW or you may be even reaching 180 before GBW is attained. So for the safety margins, that 40 we know is 45 per decade, so even if 1 decade shift is there you are just at 180, okay. If the pole is for 1 decade ahead earlier, then you are actually hitting 180 point, and any problem starts in parasitics, because in the circuits we believe that we have assumed all the parasitics properly, but there are metal lines in actual chip, there are metal lines, there are poly lines, there are metal oxide metal lines, there are mini lines. At some nodes they may contribute to some parasitics, okay, and those each capacitance will give what, another pole, and let us say it happens to be earlier than this, then your stability criteria is in haywires, okay. So at least 45 will save you up to 180, okay, another pole will come, so okay 180 will hit, so you are still in the margin of safety. You may say 30 degrees also safe, 10 is also safe, yeah, I am not saying it is not safe, but for the circuit performance to be guaranteed, the minimum phase margin you should keep is 45 degrees. Please take it 0 above everything is safe, even if this point is reached just here it does not matter, okay, because it is fair enough that it is still not positive feedback, but that may change because of the other parasitics. For example, even the gains which you thought on a single chip, it may some devices may have different W by or different parameters, and the adjoining transistor or adjoining other chip may have not the same values, variability, which may again push you to other values which may actually have, that means some chips will be stable, some may not be, and that risk we cannot take, okay. So the minimum phase margins you should hold for any amplifier is 45 degrees. So please do not think that 0 is not safe, 0 is safe, 0 plus, okay, safe, but safer is 45, it is higher, it is even safer, okay. Now to make it higher, obviously you can see if this pole occurs even far, not from here but somewhere here, that is even safer, because the second pole 135 value will now reach even closer this, and by then gain bandwidth has already more than 135 degree it is showing, okay, that means more than 45 it is showing. So if the pole second pole occurs beyond gain bandwidth point, safer for you, always safer for you, but minimum it should occur is at the point itself, because the pole should not start or second pole should not start earlier than gain bandwidth, because otherwise that 45 degree is in risk situation. I am not saying still it is safe, if it is close to that still it is safe, but not very safe. To be 100% safe, I would prefer the second pole should be outside GBW point or at least at GBW point, is that clear? So why we always look for that GBW point is at this point we are looking for phase, because phase margin is measured at that point, is that correct? So at that point we like to see whether sufficient margin is provided for me, so that the loop gain does not allow you positive feedbacks, is that clear? So that is the way all stability people start looking into it, is that clear? Now this case is shown only for 2 poles, if there are multiple poles, multiple problems, but in general there are techniques which we have learnt, splitting poles or nulling the poles or nulling zeros. We can do tricks to actually get rid of some of these poles problems and still can attain what we call stable amplifier, is that clear? The 2 techniques which we will use later in my design, one is using the pole splits, the other may be nulling the pole itself, okay, by 0. So this issue, why this 135 or 45 should be very clear, that why keep everyone says 45, 45 is not sacrosanct otherwise, but one pole, another pole may give you another 45 per dB decade, that may create huge problem for you in stability, and to avoid that always go beyond 45. So the minimum phase margins which amplifier use is 50 degrees minimum. Then you may say, can I use 90? Yes you can, but then what else will happen, we will have to see if you keep increasing phase margins, does it affect something else, okay, and if that affects, then we will have to go back and say okay, reduce the phase margin. So it should preferably, I may show you later somewhere, that between 55 to 70 is typical phase margins are used in almost all analog amplifiers, is that correct? 55 to 70, 72 some designs are, but around that value and not beyond 75 anytime, okay. Is that clear to you? So these are not figured out by just by, we do some evaluations, we do some experiments actually on chip, and we by knowing parasitics now we figured out, okay, this is the range at least you should hold, so that stability is guaranteed. Please remember, we are always thinking of two pole system. If there is a third pole, more values, more problems may come, to see to it that the third pole actually never occurs before GPW at any cost, okay, at any cost, okay. That should be moved away or removed, moved away or removed, whichever way you can, that is the best for you, okay. The technique which I do not know my second year students remember, but just to give you that interesting figure which we use, you can always find from the open loop, need not plot loop gains, okay. Of course the assumption in all this decision is beta is independent of frequency, easier to do it. You can see from here log A beta essentially can be written as log A minus log of 1 upon beta, maths, nothing great, nothing simple. Now if that happens, now I plot log A, I plot A as the normal open loop gain. So I, let us say quickly, let us say right now two pole system, okay. This is my A open loop, okay. Then I, assuming beta is constant, which in our last case is not, but in case it is resistive feedbacks, I can put log 1 beta is one value because the beta is constant. So I draw a line somewhere here which is log of 1 upon beta. So what is this value? Loop gain, this is the loop gain. So what is this value therefore? Loop gain is 0, is that point clear? This is the point where loop gain is 0. Now if you take the phase for this, it will reach 45 degree, this will reach 135 degree, and as long as you are within this range, your feedback 1 by beta point, you are always more than 45 degrees phase margin you can create. Is that clear to you? So the, what is the thumb rule? If you have an open loop gain, see to it that your feedback does not go beyond second pole, it should be within first pole and second pole. If you can fix your this value there, you are 100% stable. Is that clear? So that is how actually from the Bode plot, by just looking you can say, oh, it's stable, okay. So this is the technique which normally many books show, but I thought that you should know why they show, they instead of showing T or A beta, they show simply this, they say okay, this is this at this point. So anyone between this, if your 1 beta 1 log 1 beta lies, then you are always safe because you are not going beyond 135 anyway. So 45 below you will never reach, and therefore you will always be safe in this. So a thumb rule is adjust your feedback such that you remain between first pole and second pole. As long as you maintain that, you will be safer, okay. So these are some tricks of the feedback networks. Those who have done control theory, that it may look trivial, but that is what we say. There are different way of looking things. Bode's plot actually gives you some idea of numbers, and that is why I follow Bode's plot. Now if you say I can have phase margin of 45 above, okay, the issue is not still trivial. There is another problem seen because Bode plot is what kind of response you are looking? Frequency domain, you are always in frequency domain. But if you see, much of the amplifier properties are actually found by what response? Step response. That is how we actually evaluate how the outputs will properly go with the inputs, okay. So here is a time domain analysis if you do for the loop gain, okay. You say you are sorry, it is V out by AV0, So if you vary phi m from 45 to 90, which is what you said by stability is the range up to which you should work, and if you plot the output, this is called, what is it called, normalized output versus normalized frequency or time. Now if I plot this, I figure out for different phi m I have plotted V out, okay, normalized V out. 45 degree is this. So at 45 I figure out there is a ringing going on. You can see this rises and comes lower, and it may take more than, I have only showed in one, but it may take 2-3 rings to finally settle. Okay. So this will be settling time, okay, this will be a huge settling time. Okay. If I increase phase margin, which I did, of course these figures are not up to the scale, these are just a representative scale. If I go for 55, I figure out that the peak goes down and it also reaches the constant point faster. I have increased to 60, I find very little overshoot and it dies down very fast. This dies down come from what? Is the damping factor, which in the second order function 1 upon 2q as we say is actually a damping coefficient. So we figure out that if phase margin is around 60, the damping is so that it reaches and almost settles to V0. If you increase further 70, it takes even longer time now to, it may not ring, but it may take longer time to settle, and if you go further it may not reach or it may take long enough to settle. Is that clear? So if you see this time response and you look your stability issue, where would you like to peg your phi m? Somewhere between 55 to 70 at best. Is that clear? So in this range phase margins are always chosen. Is that clear? Because then I am assuring you that output will not ring, even if it does little bit, it dies down very fast. This is our second order, any nonlinear system you study, any transfer function, and this can be proved otherwise. Is that clear? So why phi m 45 to 70 or 55 to 70? Because I figured out that other than the other requirement which may occur, even the time response may create an issue, which at time, please remember here I am only showing you say 1.4 times. Sometimes if you lower, you can see this may become twice, and then it will take hell of time to settle, and within your time frame it will never settle. Is that correct? So lower phase margins are also risky for even settling times. Is that clear? And therefore we always prefer from the 2 points. One is of course the stability issue. 45 is a marker, so I say okay 10 degree above or at least 5 degree above. Okay. So 50 to 70 is all that I should look for in my designs. Is that clear? So you must be finding that every time I stick to 50 to 70, this is the reason why I am sticking to 50 to 70. Not that I cannot design at above 70, not that I cannot design below 45, but the risk of stability and transient is very obvious, and I must look into both before I decide what margins I have. Is that clear? So this issue, which is not, some books do, many books do not even consider that why. So I thought from the second order transfer function theory, you can see, you can evaluate how much is the range really available to you. Is that clear to you? So please take it that these values which I choose, yes. Yes, this is omega t is time response. Omega is radian per second, so omega t is radians. Okay, due regards, Kale, that is theta. Theta is in time frame. Okay, so having decided that in all my designs I will keep phase margins between 55 or 50 to 70 and not go beyond. Is that correct? Or no, not go below these two values. So bound I have already fixed. Okay, this is my range up to which. So any design now I will do in amplifiers or OPAMPs or anyone, this factor will tell me whether I am okay or I am not okay. Is that clear? So the first thing what is the design thing will be, in design analysis what we did, we actually were given function and plotted and figured out what is phi m. In real life what will be this, they say okay this is the gain, this is this, then I will have to make my choice, okay this phi I might choose, okay, and then I solve. If I meet all my specs I am still stable, thank you very much, otherwise change my phi, do it again till I satisfy everyone, okay. That is what design is otherwise. Is that clear? In phase margins are never specified, that is your design spec, that is what you will control, okay. Okay. So before going to that, today we are going to hopefully solve the OPAMP issue, but before OPAMP actual numbers we come, let us see the analysis part as well. This is a typical two stage single ended OPAMP with parasitics available. I think this C1, C2 everything last time I already explained which values of capacitance as to C1 and C2. Only thing now I added is C3, okay, and we will see whether that has some influence. If not, we will just forget about it, okay, but we will figure it out. We will not like to say C3 has no influence, okay. When it will not have any influence? When the time constant associated with this becomes extremely small, RC time constant is very small, then what we will say that the frequency at which it will come, it will be far away from GVW, so damn care, okay. But if it does, then we will have to actually figure out this pole as well. 99.99 this values because of the W by L's parasitics available to you, always safe enough to think that C3 does not affect, but we will solve that also, okay. So this is a M, please remember this is a DFAM, you have Vn input here, and the current in M5 which is your ISS current for this is decided from the mirror side, okay. We will actually show final circuit for OPAMP, there we will put the bias circuit here itself. So what M5 decides? The mirror current coming from the mirror, because there will be a whatever I parallel it will come here, and that is which value I will choose here, I will choose the ISS, or what we call I5 current is the major current making all decisions for us, okay. Why it is making most decisions? Because we will see later this will not only decide the GMs, this will also decide the slew rates, okay. Therefore and also power dissipation, so everything is going with what current I choose at M5. So another parameter for my design is I5 or ISS, okay, that decides my everything. So I like to see what sizing M5 I should have to create as much current. I may have mirror any size, but I should have to mirror here with that much current which is my design parameter. Is that clear? So the issues are now getting clear, okay, that I must look very carefully what M5 size comes. I also should see that C3 RC3 is not very important, and then I move ahead. Now I say okay this is a DFAM, the output of DFAM which is single ended because this is diode connected loads is fed to the P channel driver which is M6, and right now you may forget CC, or you may right now maybe you can put dotted lines on that if you wish. This is the which is what is the purpose of CC? It is the feedback capacitor which we are putting between output and the input, is that correct? Now this is the input, this is the output, so we are actually giving a feedback for the gain stage, okay. This C1 we already said is the bunch of all capacitances which last time I had, right. Same way I have said C2 also has all the capacitor plus any external capacitor this, okay. There is the issue, we will see that if this C2 is a function of external load you have a problem. What is the problem? That means something else I connect, I will have to redesign, and in chip nothing can be redesigned, okay. As of now we will think yeah C2 is known and does not vary, how do we get rid of this? We will see whether there is a possibility. Is that point clear? My worries are chip is once designed, there is no something add on there, so that is it. So you do not know, so okay then you have to design, over design for something, and over design means oversizing, over power dissipations, which means you have paid a lot of penalty for doing nothing, okay, which may never actually come into picture, but it comes then you should be ready, so you actually thought and put it. So if you know it, it is independent, it does not influence so much, then you say kuch bhi aage load ho mere ko kya hai. So let us see how we do that. That is also another problem which op-amp designers have to look for. This C2 influence, though looks very strong, should be actually not as strong. Okay, how much I can do is our game, because I remember C2 will contain capacitance external to the chip itself, which it will drive next. Okay, so this is typically another thing you should, other day someone asked, so I may clarify for those, for others 99 probably knew and therefore did not ask, or did not know and did not want to ask either. Someone was saying, is this current and this current is same? It will not be, it need not be. The current is decided by M6, is that correct? Because GM of this is going to decide the gain's outputs. So what current this is going to pass has to pass through this. So if whatever current is passing here, if they are same, jolly well good, you put 1:1 ratio, otherwise adjust ratio here to get this current. M7 is not deciding the current here, M6 is deciding the current, M7 gets it and then it figures out if I have gate connection in mirror, what sizes I should keep so that this current translates into this current. So please remember, though biasing looks to be from this side, current source side, it is not decided from this, it is decided from the GM of this M6, is that point clear? GM of M6 is going to decide the gains, bandwidths, so whatever you should wish to pass here will pass here, and that must be adjusted by W by L to suit mirror requirements, is that clear? So never think इसको इधर कर दिया तो यही करंट यहाँ, ऐसा नहीं है, यहाँ कुछ भी करंट हो सकता है which will be decided by M6, is that clear issue? So this last time after the class some two gentlemen came and they were asking, so I thought maybe clear for today that M7 is not mirrored biasing, though it is mirrored, but it is decided by M6 current requirements, is that clear to you? Okay. So it may happen in some cases they may be equal, but in some cases they may not be equal. For GMs you are requiring different here, so what can you do, is that clear? So please remember, these are design issues we should keep in mind, because these designers should be the best analysis people, because they know what hurts when. That is why designers should also be able to solve problem correctly, because otherwise they do not know which is hurting us most. Okay. We have done this, again I repeat for you, this the equivalent circuit of two stage op-amp. This is my GM1 Vin, this is RO2 parallel RO4, C1 CC GM. We will also see two cases, CC removed and CC put, GM6 V1 RO6 RO7 C2. Okay, this is the AC equivalent circuit of two stage amplifier, and I think this last time if I have not written, please write down, these are the C1 C2 values, which means in real life once you decide the W by L's, you will have to verify whether this is reaching C1 and C2 values. Okay, so there is an issue, so this gain function is going to decide C1 C2 values. So there is a loop kind here as well, adjust your C1 C2s. Okay, okay. Please note down, because these are, but of course these are given in books, so it is not that I have invented or something. Just see the transistor and at that node which you are looking, which parasitic capacitance for each transistor comes there. Please remember one more thing, circuit wise you must know, unless the second terminal of the capacitor is AC grounded, that node does not receive any contribution from that capacitor, is that point clear? At this node a capacitor is sitting here, and if this is not grounded, this does not play any role, AC or DC. DC means AC, for AC it is ground, is that correct? So unless there is other end is going to be grounded, at that node they do not add to. So only those capacitance, like if the substrate is not grounded, let us say floating, then the CDBs and this will not be there, because substrate is not actually grounded. So those capacitance does not exist, is that clear? So please verify that all those nodes at all the capacitance at that node, the other end of them should be AC grounded, even if it is DC means AC grounded down, okay, and this is a compulsory requirement to add any node any capacitances. Okay, everyone has written down C1 C2, but what are C1 C2? I thought maybe I will explain. Normally books do not give C1 C2, I only thought that you should know what C1 C2 actually are coming into our picture, okay. Of course some books may be giving, ऐसा मेरा ये statement गलत हो सकता है. This is CGD 6, वो थोड़ा 5 6 में confusion था, this is 6 7, what, हाँ V1 is across C, that is the input to the gain stage, okay, that is the input, this is all AC, huh? Though it may look capital non-capital, all are ACs. There was confusion, I have once told you, now onwards unless said otherwise there is no DC, we are only solving equivalent circuit, all are AC components, okay, is that okay? दो नोड हैं, दो इक्वेशंस लिखी जा सकती हैं using the Kirchhoff law, nodal analysis, GV plus I plus G, whatever it is, I wrote the equations for the two nodes at V out and V1, there are only two nodes V out and V1, so I wrote this equation. From the equation 1 I evaluated the value of V1 because I am interested in Vn and V0 relationship, is that correct? So I replace V1 from this relation from here, okay, then V1 is essentially equal to V0 SCC GM1 Vn bracket R1 upon 1 plus R1S C1 plus Cc. Do you get the one? These are just corrected the terms and figured out what is V1. V1 occurs here, V1 occurs here, V1 occurs here, this does not have and this does not have, so only V0 SCC minus G1 V1, this R1 is multiplied everywhere and then you get this expression. If I substitute this into second equation, what do I want to eliminate V1 and only get relationship between V0 and Vn, so remove V1. You just someone asked us, so where is V1 is the output stage, first stage gain, first stage output, that we figured out, now substitute into second and then write the same GM6 into V1 plus V0 by 1 upon R2 plus SC2 plus SCC minus SCC, again V1 is appearing here, so minus SCC R0 V0 SCC minus GM1 V1 upon this. Now again there is an issue because there are V0 terms here, there are V0 terms here, so collect V0 terms and then on the right get Vn terms, divide V0 by Vn to get your gain, is that clear? ये V0 term है, ये V0 term है, उनको जोड़ो, बाकी को सब दूसरे तरफ, okay. Okay, if I do that, is it okay? I want to write, why are we doing all this? I want to design an OPAMP, so I am trying to correlate the gain function, the slew rate function, power, everything with whatever spec I have, okay. So I am trying to get the relations, and what is the major relation I will get from this? The poles and the zeros, because they are going to decide some way my GMs, okay, because pole is essentially a GM by C. Now that means GM is now decided not just by a factor but also decided by the poles available to you, and that is why we are interested to get those expressions, is that correct? Is that okay? So we get the transfer function of gain V0 by Vn, of course to be precise you should write, it is AVS, so it is the transfer function, and as most books, this is taken just to convert it to what books give, so I figured I made Swayam constant as they have given in the expression, so that it looks identical to second order system which many books actually tell, okay. So we wrote M is equal to GM1 GM6 R1 R2, N is equal to R2 C2 plus CC R1 Cn plus GM6 this, oh there is no S here, Q is R1 R2 C1 C2 C1 CC C2 CC. इसमें से टर्म कलेक्ट कर ली है मैंने और तो कुछ नहीं. So I have taken GM1, GM6, R1, R2 outside. So I get 1 minus GM1 this, so एक GM6 है, sorry. So then we get 1 minus SCC by GM6. So how the transfer function looks now? It's very familiar transfer function. Something on the top is trying to give you 0 and something from the denominator. Since it's a second order term, I am going to get 2 poles. Please remember each capacitor contributes a pole. So there are 2 capacitors C1, C2 used, so there should be 2 poles, second order system. So AVS is M times 1 M in the bracket 1 minus SCC by GM6 totally divided by 1 plus NS plus QS square. ये GM R1 R2 ये बाहर दोनों साइड से निकाल दिए गए इसलिए कट गए वो सब. Is that okay? This transfer function is very familiar, so I thought I should represent a second order stand. If you see, this Q is essentially the term which you will get there, the only difference is Q is used with N, okay, and 1 upon 2Q they write, which is the 2 zeta, or zeta is the damping factor. So I did not want to correlate there, but I just made some second order system. Okay. Please remember whatever goes with S is 1 upon 2Q, and that is the zeta. Zeta is damping. What you see ringing is essentially for the zeta factor. That phi m can be therefore represented in terms of zeta. That is exactly what we are saying. So that choice of phi m is related to your zetas. Is that okay? Everyone has the formulae? We are still not done design, we are still working on analysis, but some issues which we will want to clear. So if you see the denominator AVS, it is 1 plus NSQS square, which can be written as 1 minus S by P1 into 1 minus S by P2, partial fractions. I expand it 1 minus S by P1 S by P2 plus S. ये टेक्निक सब बुक्स में दिया है, every controls बुक्स में दिया है, but I just thought I will do it for my own sake. मैं भूल गया कुछ चीजें तो. So if I expand this, I get the only thing I made, I mean of course analog people know this. I said in general the first pole, which is my dominant pole, is much higher, I mean much away from. If I take such decisions, then it is easier because the second term then I can leave it. Okay. So I say it is 1 minus by P1 S square P1 P2, then P1 is, because this is N, so it is minus 1 upon N, so and then that is 1 upon P1 P2 is Q, so P2 is minus N by Q or 1 upon P1 Q. So now I have both poles available to me, P1 and P2. Okay. Since I know N and Q, I can now substitute N and Q in terms of P1 for P1 and P2. N and Q in what terms? R1, R2, GM, C, all. So now my actual circuit components will actually appear. I need not have done this. I could have, you if you are smart enough, you know which term, from where you can see those terms, from 0 time and constant value you can actually know which terms are coming. Alternatively solve Kirchhoff law and get the same relationship. What is the problem? Why I said I do not want to do 0 value time constant for this? Because I will miss the 0. In the 0 time constant situation you always miss the 0. In our case 0 has a very dominant influence, okay. Therefore I did not show you the other technique, but poles still can be figured out by using 0 time constant values, both dominant by open circuit and short time, short circuit you can evaluate. So using this I have the pole 1 upon R2 C2 C plus R1 C1 CC plus GM6 R1 R2, which is my denominator now for this P1. For typical amplifiers GM6 is quite large, so therefore GM6 R1 R2 is larger than R1 plus R2, so it is only this, and this is always larger than R1 C1 into R2 C2. So one may say GM R1 R2 is greater than R1 plus R2, or to say P1 can be just written as GM6 R1 R2 C3. You can verify this is what the value you will get from 0 time constant method, okay. So that you could have directly figured out, but this is what it is. And therefore please remember pole has to be negative, is that magnitude wise, magnitude we say positive, but actually it is the negative value which you are getting. Pole, what does that negative value means? On sigma j omega axis pole lie on the left half plane, okay. That is one of the criteria we will do. Nyquist criteria says as long as you are minus 1 0 you circle and the pole is within, you are stable, otherwise not stable. So that is exactly what we are achieving. By now figure it out P2, okay. I also should say CC is normally larger than C1 and C2, okay. C2 is larger than everything, but this is larger. So we say the dominant pole will come from GM6 R1 R2 RC CC. So this is the dominant pole. The second pole which is minus n by q or plus 1 by p1 q, okay. The first pole, and therefore substituting that I get the second pole. We assume that C2 is larger than C1 and CC is also larger than C1, then P2 pole can be roughly written as GM6 C2 CC or GM6 by C2, which also you will get from 0 time constant technique. So you need 2 poles from the second order function, so you got 2 poles. Could you now see this is an issue, that output capacitance, because P2 is decided by GM6 and C2. If load is higher, this pole shifts left side actually. Yes, manager लिखा है वो सही है. Okay, and we also have said that a 0 exists, which is the 0 part of the numerator, which is GM6. Everywhere the gain, please remember where the feedback is going on, at the gain stage. The poles are hit by the gain stage, and the first one which you are saying should come from C3, but that I will show you that I am not looking into them. Okay. So rewriting whatever I wrote here in nutshell is the following. वो लिखा है फिर से एक final version में दे रहा हूँ. If you are not written, you can write down here. The gain function is m1 minus SCC by GM6 1 plus n and q I already m n q I already defined. The first pole is minus 1 upon GM6 R1 R2. The second pole is GM6 CC upon this. And since C2 is greater than C1 and CC is also greater than C1, this is GM6 by C2. And finally, this we already derived, I am just trying to summarize it, and there is a 0 which is GM6 by CC, is that correct? So you have 2 poles and a 0. Okay. Yes, you want last sheet? No, they are just restatement in nutshell. So how do you calculate phase margin for such this? I have figured out phi m is equal to 180 minus phase of each of these P1, P2 and Z, okay. But what will be the phase of Z? Plus 45 degree, that is minus 45 degree. So what we do is tan inverse minus is tan minus of tan inverse, उसका advantage लेकर उसको flip कर देंगे, W by Z की Z by W, उसका उल्टा कर देंगे. So let us see it now. Is that okay? Everyone has written down. I repeat, this third last one is Z1 is GM6 by CC. P2 is GM6 by C2. This is the relation I am going to use. Please check it. The 0 is at GM6 by CC and pole, second pole is at GM. Please remember phi m is decided not by P1 so much, but by P2 position. Where is it? So this is C2 and this is CC, and they are going to decide how much stable I will be. Is that okay? Is that final? लिखा सबने? So if I have 2 poles and a 0, last time I said, the phase margin I wrote there is tan inverse omega by P1. Of course it should not be called omega, normal phase. Phase margin should be written at the omega at what point? Where you measure this should not be M, this should be only phi, but phase margin is chosen where, when the frequency is at GBW, is that correct? So we write, so this need not be called M. Phi M generally, because of the GM and CC values, Z1 will be far away from GB. Okay. So by the time if the second pole has already gone to minus 80 dB or minus 100 dB, so another 20 dB plus will make it minus 80 dB, but it already you are well within your margin side. So you are not worried because the gain has fallen down sufficiently below and then 0. Please remember 0 will push the gain plus 20 dB per decade, but if it is already minus 100, so okay, 80 dB is also okay, fair enough. Okay. So that is something you have to understand, that this 0 should be away from this. We will check this for different value of Z, how much phase margin we can evaluate. This is one problem we will solve. Okay. So please remember this, I changed tan inverse GB by Z1 because I said it is all are minus, because otherwise it should have been plus Z by W, so I inverted it. So I have to now calculate, what do I calculate from here? No, I will assume phase margin. I will check it, what is this? I will assume this, and then what I will get? P2. So I am only interested in P2. I will say this always known, this I will make it known, then I say okay, all that I need a relationship between gain bandwidth and P2, because that is the one which is deciding major this for me, stable or not stable. Is that clear? So the tricks of the trade is fix this somewhere better, this will come nice easily, you know how. If you know this, for this given value I get a relationship between P2 and GBW, that is what essentially. Now P2 has GM6 by C2, is that correct? Gain bandwidth, gain is known to you, P1 is known to you, so the bandwidth is known to you. So you know GBW, so from this I can know if okay, I can get C2 or relationship between C2 and others, and therefore I can say W by GM6 का क्या होगा जो उसको fit कर दे, ठीक है? That's all that design is about. Okay, is that okay? Yes, I told you ना madam, it should be Z by W. Tan inverse minus of tan inverse is same, so उसका उल्टा किया है. Okay, tan थोड़ा trigonometry. Okay. Now before we quit this area, before we start OPAMP design, there is an issue. This was all done with CC available. I should have done the other way, isn't it? Without CC kya hai? So let us do without CC. If I remove CC, I can see my input poles and outputs without any calculus, zero time constant technique. I know the first pole is 1 upon R1 C1, the second pole is 1 upon R2 C2. Is that correct? Since C2 is larger than C1, what will happen? R2 R1 may be same, is that correct? C2 is larger than C1, we do not know right now. Why? Because that feedback was adding to C1 now. This may be something different than that C2, is that correct? वो 1 plus AV0 देखा था ना, अब वो term नहीं है, तो अभी कौन छोटा है कौन बड़ा, we'll have to check really by the values. Now if I have this new poles with CC removed, is that clear? No feedback, that is open loop system, AOL. Okay. Same equivalent circuit, the CC here has been taken away. Okay. Now, थोड़ा interesting case हो रहा है CC लगाने का, वो will, what is CC is also called Miller capacitor. No, compensation is doing, but it is essentially Miller capacitance. So the compensation is also called Miller compensations, okay, because it is a Miller capacitance which is doing the job, it is called Miller compensations. So if we have a CC, the two poles are P1 dash is GM6 R2, and just to make equivalence correct, I put R1 C1 upon C2 CC by C1. and P2 dash is GM6 by C2. So you can see from here, in the earlier case it is P1 is only 1 upon R1 C1, is that correct, without Cc. GM6 R2 is gain, so obviously, and this Cc is larger than C1, so obviously these quantities P1 dash is reducing. So P1 is larger than P1 dash, is that correct? However, if you look at P2 dash, which is 1 upon R2 C2, but we know R2 is R01, R06 parallel R07, GM6 is always larger than 1 upon RO, because they are in mega ohm, this is in tens of kilo ohms, okay, 1 upon GM. Okay. So what does that mean? So I can always say P2 dash magnitude wise is much larger than P2, is that correct? So what has happened? P1 has reduced P1 dash by Cc, but P2 dash has magnitude wise enhanced, is that point clear to you? P1, let us say it was somewhere here, it moved to okay, I will show the figure and then it will be much more easier, you figure just this word which you often use in Miller compensations or Miller capacitance is split the poles, okay, it is called splitting poles. Okay. Yeah, but that is what I said you also, C2 is normally higher simply because the load is sitting there. If unloaded case में ये issue आ सकता है, but normal में external कुछ ना कुछ होगा, वो उसको हमेशा ऊपर ले जाएगा, that is the reason. But I do not want that so strong dependence, which is I will remove that. I do not want, I should know a priori what is the load, okay. So I will try to see what you are asking, कि इसका थोड़ा झटका कम करो, okay. Let us see how do I do it, is it okay? So if I show you on the figures, now this gives you everything in nutshell. If I see now loop gain sigma j omega on this scale, complex scale or complex graph, my 0 is positive, so sitting here, my dominant pole was P1 R1 C1 which was here, and my next pole is R2 C2 which is here, okay. Now these are like this as before Cc applied. When I applied Cc, I figured out P1 reduced or rather reached the other side, so P1 dash reached here, but P2 actually enhanced the other side, so P2 dash reached here, P1 dash came closer to 0. So even if P1 P2 were closer, by putting the Miller capacitor I separated them. So one of the case we are all the time saying that there should be a dominant pole is guaranteed if I put a Cc capacitance. In natural system Cc exists, from where CGDs exist, so partially आपको split करता ही है वो, okay, because CGD is always sitting there, but that value is very small. This Cc may not be that small, actually you may actually decide to put extra capacitance to suit your split requirements, is that correct? So do not believe that CGD is sufficient, in some cases maybe, I am not saying it will never be, but generally it is not, okay. If you use that CGD, your phase margin will be close to 45 and then you will have a problem. So you want phase margin to be at least 55 or something, and that is my worry. So let us look at the loop gain Bode plots. This is my original pole P1, this is my second pole, okay. If I put the plots for phase, you can see at the first P1 how much should be the phase, 45 degree down, so this is 180, so I must reach 135 at P1, is that correct? And second pole is away, so it goes down and reach till 90, it remains till second pole it sees, and when it sees second pole at that time it should become another 45 degree which is 135, that is 45 here, okay. Now this 45 is at the second pole, is that correct? And if I extend it down, you reach at this value at GBW, you have a very marginal phase margin, still I would not say it is unstable, but very close to instability. Is that okay? So if I do not put Miller, I may have a situation, of course this still depends on C1 C2 values, but typically if you see, it may have, worst case may be that you may actually get 0 phase margins kind of thing, okay, or close to that, which is unsafe to a great extent. Is that clear? Now I say, since CC causes pole splitting, so P1 dash तो कम हो गया. So we first pole now with CC is reached here. The P2 which is away, now we can have a choice. We can initially at least say that this P2 dash should be at the gain bandwidth. Where? At the gain bandwidth point. Why did I say so? Because at least at that point then 135 degree is what I am expecting, so 45 degree at least I am getting that. Is that clear? I repeat, this P2 at least should, or not before, it should cross GBW point at best, at least, okay. Because at this point then, if I plot this, I at least have 45 degree phase margin. Is that correct? Because at that second pole I should get 45 degrees, so the minimum margin I now reached is 45. So the ये भी correct होगा कि नहीं पता नहीं. So what should I do here? This should continue to have minus 20 dB further, and then the second pole should start, in which case this 135 point will be somewhere here, so the margin will be larger than 45, and then you say, sir, we are safe, okay. So this pole, how much to split is also, the problem starts somewhere else. If you keep splitting too much, this P1 may actually go into the right half plane. So you can't put CC as much you like, and you suddenly find instability created because of the P1 itself, okay. Is that clear? So ठीक है, अभी तक all this talk में हमने क्या बोला, as if this doesn't exist, zero doesn't exist, बहुत दूर है, कुछ नहीं कर रहे, इसके साथ भी कुछ कर सकते हैं. If we can play with Z, then I have another parameter for phi m, okay. Now this part is what we say controlling right half plane poles, controlling right half plane zeros in a such a way that this CC requirement is slightly reduced. Is that, otherwise what is the this, you increase CC, feedback increases, this will further go down ahead, because you want this second pole should cross GBW, so you will prefer what, larger CC, but then this P1 should not hit the imaginary axis, okay. If hits imaginary, it is still okay, very low bandwidths, but at least stable, but if it crosses, then you have a problem, you have a zero, equivalent zero on that, okay. Now this is an issue which makes something else you must think. Is that clear? So it is not just C, must be something else there which may change the poles, okay. So I may add another equivalent pole or zero, whatever I will call, so that CC is not increased very much, because then I do not have to play too much with this, but still my cutting point is much away from it, so that I say I am safe now, okay. So this is what we will do. The method I already explained. At the pole from the top value, the slope 45 per decay means 45 degree it should hit. It should continue till 90, because J vector says 90 degree. But if the poles come before that, then even there itself another 45 should start, because that much slope should change 90 dB then and start decreasing right there. But normally we assume they are away, so we are allowing this to settle at 90, and when the second poles appear at this point another 45 must show. So that is how you graph. Without this we see that phase margin is close to 0 or plus, but with CC you have shifted, because of the splits, we have shifted the P2 points such that we are larger phase margins are possible. Infinite किया तो क्या होगा, यहाँ पोल दे दिया तो ये P1 भी उधर 0 ही हो जाएगा, इन्फिनिट नहीं कर सकते, सेफेस्ट है ना, अभी तो कोई हमेशा स्टेबल है पर बैंडविड्थ नहीं है, तो थोड़ा सा खेल है। इज दैट ओके एवरीवन? ड्रॉ द फिगर, थोड़ा कठिन है, मुझे भी काफ़ी समय लगा बनाने में, वो इसलिए लगता है कि ये इसीलिए मैंने वो ग्राफ बनाया थोड़ा सा, because otherwise just drawing that becomes difficult. Okay. So you always draw lines so that you know where to draw things. If you are really calculating value from this, don't, because then you actually take a graph and then put on, because this is not, of course these are called log scales, these are linear scales, so log semi log paper आपको लाना पड़ेगा. So phase margin improvement के लिए CC होना बहुत जरूरी है. Okay. Is that this issue is clear? Last slide and then we'll stop. We'll start with this. Is that clear to you? As anyone has a doubt now that why CC? CC is one which is controlling. Okay. Now next slide. Everyone. So in nutshell, what did we say? The bandwidth, gain bandwidth point GM1 C1 plus CC G1 plus CC and P2 to GM6. The minimum phase margin 45 degree forces you GM by GM6 CC by C2. Is that correct? This is equal, that is at the point where phase margin is 45. So at least you should not go beyond this. Preferably what you should do, GM6 by C2 should be greater than GM1 by CC. Is that correct? And if that happens, you have larger phase margin to play with. Is that correct? Right now what is the minimum, the corner case is GM1 by CC must be equal to GM6 by, please remember the gain bandwidth is something to do with the diff amps drivers, GM1 or GM2, they are equals. Okay. So GM1 by CC is the gain bandwidth, actually it is C1 plus CC, CC is larger than C1, so GM by CC. So the ratio of CC to C2 is ratio of GM1 to this. Is that clear to you? So we must be now from the all that phi m value you choose, you probably get some ratio which will be able to get ratio of GMs, and GMs are proportional to currents, so you will get the ratio of currents, that, and currents are proportional to sizes, so you get the ratio of sizes. Okay. Okay, we can increase CC but we lose bandwidth, hence to avoid reduction in bandwidth but to improve phi m for stability, we can control right half plane 0, okay, which we are right now thought kuch nahi kiya. To bring it towards left half plane, if I somehow shift that to left half plane, that can help a lot to nullify a pole, okay, and that if happens then we say CC requirement will be minimum, just sufficient for you, and your, to do this we will see later, CC need not be alone, it should be R series to CC, this will create another time constant RCC, okay, that will give you the 0 shifts out, and if 0 shifts right half plane, left half plane, your much of the worries could be, that is you sit that pole on something, so null kar do usko, okay, that is called nulling. Okay. So this is the thing which we will do today evening. एक लास्ट लाइन शाम को जहाँ से स्टार्ट होना वो ये है. तो अभी आपको ओपैम्प का एक्सप्रेशन दिखा दिया, बुडेस प्लॉट दिखा दिया, फेज मार्जिन का रिलेशन दिखा दिया, अब मैं एक्चुअल स्पेक्स पर इनका कैलकुलेशन आपको दिखाऊंगा. इज दैट ओके? Theory has been discussed, importance of every issue has been thought at least if not discussed fully, and now actual values we will see what do we gain, okay. That will give you some idea how one gets sizes.